This is problem 6 in chapter 30, practice problem. Some students were having some trouble with it, as well did I. Let's look at that problem. We're told that an electron in a certain quantum state of hydrogen de-excite one step down to its nearest neighbor quantum state. So we're starting out at an unknown quantum state labeled n. The electron shown there de-excites down to its nearest neighbor state, n minus 1, and in the process emits a photon whose energy is shown there. Our goal is to determine the transition that occurred from what to what. And so we will have our answer as soon as we know the value of n. So we need to create an equation involving n. The foundation on which we'll stand in order to create that equation is conservation of energy. In a system, the total energy earlier equals the total energy later. So earlier, or before the transition occurred, the only energy present was the energy the electron had, which is found according to the 13.6 rule. The energy before in our system, negative 13.6 over the quantum index squared. After the transition occurs, there are two things that are now in that system. The electron, now in a lower line energy state, and the photon that was liberated, emitted, as that transition occurred. So later there are two entities that have energy. Add them both, and that will be the total energy. But that total energy after equals the total energy you had earlier. And that earlier total energy was just the energy of that electron in the original state n. And so we set up an equation that puts the after total energy equal to the earlier one, or rather vice versa. The early energy before is negative 13.6 over n squared. That's before. After the equal sign, we have the energy of the two things after. The new electron energy in the n minus 1 quantum state, plus the photon energy that is liberated. I'm leaving the units off in both places to save space and time. Now we come to another challenging portion of this problem. Solving that equation for n. We don't want to do it longhand, that's too hard, takes too much time, and it's not physics. So we use the solver feature or a calculator. Well, it's a quadratic equation, n to the power of 2, and so there are two solutions. Often in such a situation in this course, when there are two solutions, one is physically meaningless and the other is good. Well, if you're not lucky when you choose your starting value for your search, what I call the seed, you'll get a bad answer, and I did initially. In fact, what I got was an infinite loop. The calculator kept searching and searching and searching, couldn't find it and kicked me out. Disappointing. Then I chose a different starting value. I believe it was 0. And when I did that, what I got was a bad answer. I got approximately 0.5. 0.00000 plus some junk at the end, almost 0.5. Well, n can't be 0.5. The quantum index n ranges from as little as 1 up to whatever, but n is never less than 1. In fact, we would have rejected an answer that said n is equal to 1, because you can't have a transition of any kind that goes from 1 down to a lower line state. There's nothing lower than n equal to 1, so reject that. So 2 tries by me, no answer. Then I tried a different number, starting seed, didn't give up. I chose 5. Could have chosen 6, 7, 8, probably wouldn't matter. I got an answer. 11. Starting quantum number 11. So the transition in question is from 11 to 1 lower, or 10. Now, you don't have to do it this way if you don't want to. On an exam, for example, what you could do is use the brute force method, trial and error method. The photon energy that's liberated here is rather small. And so you expect that the transition is going to occur between two states that are close together. And states are close together when the quantum index is high. You don't know how high, 50, 60, 70, 80. But what you could do is just guess a starting quantum number. Guess 15, for example. And when you do 15 to 14, you're going to get a number different than that when you subtract the two energies. So keep searching around until you luckily land on 11 to 10 that works. This is a last-ditch resort way of solving a problem. It's the way you could solve the problem if you don't understand how to set up this equation and you get frustrated by using the solver feature of your calculator. Now, there was a second part of this question that really should not have been there. Additional useless information was provided. You were told that once this electron, having arrived at its next line orbital, once it's there, it makes another transition down to its nearest neighbor. And you're told what photon energy is released in that process. It's shown here. The new initial state is the n-1 quantum state. It transitions down to its nearest neighbor state, n-2. And this is a photon that's released. You don't need to solve this equation to see what transition occurred, because you already know the value of n from the previous work. N's 11, so this state is 11 minus 1, or 10. And this is 9. So just write down right away that the other transition, the subsequent one, is 10 to 9. I hope this has been helpful. Good luck on your exam Friday. And if you have any questions whatsoever, don't fail to email me. Or you can go to the announcement portion of your Canvas, and, or rather to say the discussion portion of Canvas, and you may find students who ask questions relating to this problem and other problems, and you can converse back and forth, and I'll jump in occasionally and help the discussion along. Goodbye.